Flow sensors measure the quantity of fluid material passing by a point in a certain time. Usually the material is a gas or a liquid and is flowing in a pipe or open channel. The flowing of solid materials such as gravel through traveling on a conveyor belt will not be considered here. Flow transducers come in several types, those that use differential pressure, those where the flow spins a mechanical device, and a smaller class of sensors that use more sophisticated technologies. Pressure-based flow sensors. This group of flow sensors is based on the fact that pressure in a moving fluid is proportional to the flow. The pressure is detected with a pressure sensor. Based on the physical dimensions of the system, the flow can be calculated. The simplest flow sensor is called the orifice plate and is simply a restriction in the pipe that causes a pressure drop in the flow, much like a resistor that causes a drop in a voltage in a circuit. This sensor requires two pressure ports, one upstream and one downstream of the restriction. The flow is proportional to the pressure difference between these ports and is calculated as follows. Q, the flow, is proportional to the area of the orifice hole and the pressure difference between the two ports. The exact equation is as shown, where Q is the flow in cubic inches, C is a coefficient of discharge, which is approximately 0.63 for water in the orifice hole, is at least half the pipe size. A is the area of the orifice hole in square inches. D is the weight density of the fluid in pounds per cubic inch. P2 and P1 is the differential pressure, and G is in gravity. The flow equation is an approximation because in addition to the pressure drop, the actual flow is dependent on velocity effects, the area ratio A1 over A2, and the surface condition of the pipes. To get the correct constant C in the equation for a particular application, the flow sensor will have to be calibrated. Let's look at an example. A flow meter for water is made from a 3-inch ID inside diameter pipe. The orifice plate has a 2-inch opening. What is the flow if the pressure drop across the orifice plate is 0.2 psi? Let's look at the solution. We will use the orifice plate equation to solve this problem, but we first need to figure out the values of the various terms. C is 0.63. We can start with this value because the 2-inch pipe is more than half of the 3-inch pipe. The area of the hole is 3.4 square inches. G, we know, is 384 inches per square second. P2 minus P1 is, we know we were given 0.02 psi. And the weight density of water is 64.4 pounds per square foot, or 0.037 pounds per cubic inch. It's 64.4 pounds per cubic foot. Yeah. Now we can put these terms into the equation and solve it. Therefore, 127 inches per cubic inches per second of water flow in the pipe. To make this a more accurate flow meter, we would have to measure the flow with some other reliable flow meter and then adjust C in the equation to make the readings consistent with what we know them to be. So what you could do is use that pipe to fill up a 10,000 litre tank and time that, and then you could recalibrate the flow meter. Venturi and pitot tube. Another pressure-based flow sensor uses the venturi to create the pressure difference as illustrated. A venturi is a gradual restriction of the pipe that causes the fluid velocity to increase in the restricted area. This area of high velocity has a lower pressure. The flow is proportional to the difference in pressure between P2 and P1. The venturi flow sensor tends to keep the flow more laminar or smooth, but both the orifice plate and the venturi cause pressure drops in the pipe. which may be objectionable. A pressure-based flow sensor that causes minimum restriction is the pitot tube. The pitot tube is a small open tube that faces into the flow. The probe actually consists of two tubes. One faces into the flow and reports the impact pressure, often called the velocity head, and one opens perpendicularly to the flow and reports the static pressure. The impact pressure is always greater than the static pressure, and the difference between these two pressures is proportional to velocity and hence to flow. Common uses of the pitot tube are for aircraft and marine speed indicators. Turbine flow sensors. Turbine or spin type flow sensors, also called flow meters, employ a paddle wheel or propeller placed in the line of flow. The rotational velocity of the wheel is directly proportional to flow velocity. A small magnet is attached to one of the blades and a Hall effect sensor is mounted in the housing. The Hall sensor gives a pulse for each revolution of the blades. The fact that the bearings are in the flow medium may eliminate this type of sensor for some applications, especially high temperature or abrasive type fluids. Magnetic flow meters. If a liquid is even slightly conductive, and many are, a magnetic flow meter can be used. The magnetic flow meter has no moving parts and presents no obstructions to the flow. A non-conductive section of pipe is placed in a magnetic field. The moving field in the pipe is like a moving conductor in a generator. It produces a voltage. The voltage, which is proportional to the fluid velocity, is detected from electrodes placed in the sides of the pipe.